Writing applications that use a TPM sounds easy. You just send commands to a secure chip, right? Well, not exactly. When you try to talk to a TPM on Linux, you quickly discover a stack of layers between your app and the hardware, and that stack exists for very good reasons. In this video, we'll talk step by step from your application down to the TPM and understand why writing TPM software isn't trivial. A TPM or Trusted Platform Module is a small security coprocessor. It stores keys securely, measures system integrity, and can sign or decrypt data, but it's also quite limited. It can only process one command stream at a time, and it has very few memory slots for objects and sessions. That means if multiple programs try to talk to it at once, they'll conflict. To fix that, we need a resource manager, a layer that virtualizes access and lets many applications safely share one TPM. On Linux, TPMs show up as device nodes: -dev-tpm0, the raw hardware interface, and -dev-tpm-rm0, the kernel's built-in resource manager endpoint. If you open -dev-tpm0 directly, you get exclusive access, but you also take full responsibility for context management, which is messy and unsafe in a multitasking OS. That's why almost every modern application instead uses -dev-tpm-rm0, where the kernel handles all of that virtualization for you. Now your app doesn't talk to tpm-rm0 directly either. It talks through the TSS, the Trusted Software Stack. The TSS is a layered software architecture defined by the Trusted Computing Group. Its job is to translate human-friendly API calls into the raw byte-level command protocol that the TPM understands. Think of it as 4 layers stacked on top of each other, from high-level developer APIs down to the hardware. Let's break down those layers. First, and closest to the TPM, is the TCTI, the TPM Command Transmission Interface. This is the transport layer. It defines how command bytes are actually sent and received. Next up, and one abstraction layer higher, we have the SAPI, the System API. This is the low-level C interface that mirrors the TPM 2.0 specification directly. Each TPM command, like tpm2 create or tpm2 read public, has a matching function. SAPI takes care of packing and unpacking command structures, but leaves session management to you. It's precise but very manual. Higher up, we have the ESAPI, the Enhanced System API. This layer wraps SAPI and makes life easier. It automatically manages sessions, handles retries when the TPM is busy, and deals with policy authorization. With ESAPI, you can write cleaner code that still has fine control over what happens. And the highest abstraction level is the FAPI, the Feature API. This is the high-level developer-friendly layer. It provides simple functions like create a key, sign this data, or perform an attestation, without you worrying about handles, sessions, or authorization math. FAPI even stores keys and policies in a file system database under -var-lib-tpm2-TSS. It's the layer designed for applications rather than TPM experts. Together, those 4, FAPI, ESAPI, SAPI, and TCTI, make up the TSS 2.0 architecture. Now here's the important part. These layers are just specifications defined by the TCG, the Trusted Computing Group. Someone has to implement them in actual code. On Linux, a good C implementation comes from the IBM TSS package, known as TPM-TSS. This open source TSS implementation is used in most modern distributions. When you install TPM2 TSS, you get a set of shared libraries. That's the entire stack. Your application links against one of these libraries, and under the hood everything else happens automatically. Intel also has its own TSS implementation, but it's older and mainly for Windows and embedded systems, and it doesn't include the modern FAPI layer. On Linux, the IBM TPM2 TSS stack is more popular. There's also TSS implementations for Go and Rust. So when you call something like FAPI sign in your program, here's what really happens. Your app calls a function from the FAPI, so a high-level call, and then this is handled by the ESAPI, which handles sessions and policy. Then this is handled by the SAPI, which builds the actual TPM command buffer and sends it via the TCTI to TPM RM0, so to the kernel resource manager. The kernel resource manager then sends the command to TPM0, so the driver, so to say, which communicates to the hardware directly. It's a surprisingly deep stack for what looks like a single function call. One common stumbling block is permissions. On many Debian-based systems, access to TPM RM0 is restricted to root by default. When you install TPM2 TSS, it typically creates a dedicated TSS user and group. The device node is owned by that group and applications must be run as a user that belongs to it. So if your program says permission denied opening TPM RM0, the fix is usually simple. Add your user to the TSS group. So why isn't TPM programming straightforward? It is because of concurrency and resource limits, complex multi-layered APIs, non-standard implementations, and permissions and system integrations. But thankfully, libraries like TPM2 tools and FAPI exist to make those details manageable. To sum it all up, if you're developing on modern Linux, install TPM2 TSS. That gives you the full TSS with FAPI, ESAPI, SAPI and TCTI. Then use dev TPM RM0 and not TPM0. Start with FAPI for application level tasks. Drop down to ESAPI or SAPI only if you need finer control. For Go, you can use Go TPM and Go TPM tools, and for Rust, check out the TSS ESAPI crate. And make sure your user is in the TSS group so you can actually talk to the device. So while it might look like a simple security chip, there's a lot going on between your app and the TPM. Transport layers, APIs, resource managers, and access control. The good news, once you understand this stack, the TSS, its layers and the TPM RM0 interface, you can write TPM-aware software confidently and safely. If you need custom TPM implementations, contact us. Thanks for watching and see you in the next one.